Hi everyone, we are Ethan, and for today, we are assigned to discuss about entropy. But before we start, let me give you a motivation that every great achievement starts with a decision to try. And now, meet my members. Have you ever wondered why ice melts in a glass of water or a perfume spread across the room without any external force? Behind that driving force is a process called entropy. Entropy is key to understanding how and why energy and matter move towards more disordered and probable states. By studying entropy, we unlock the ability to predict whether a process will occur spontaneously, giving us insights into everything from chemical reactions to the behavior of the cosmos.
The second law of thermodynamics states that for any spontaneous process, the total of entropy of the system and its surroundings will always increase. Entropy is a measure of disorder or randomness, and this law suggests that natural processes tend to move toward a state of higher entropy or greater disorder. Spontaneous process. It is a process that occurs naturally without the need for external intervention. Entropy. It is a measure of disorder or randomness in a system. The greater the entropy, the more disordered or chaotic the system is. For a spontaneous process, the total entropy of the system and its surroundings must increase. This can be expressed mathematically as delta S total equals delta S system plus delta S surroundings greater than 0. Delta S system is the change in entropy of the system itself. Delta S surroundings is the change in entropy of the surroundings or environment of the system. Delta S total is the total change in entropy, which must be greater than 0 for the process to be spontaneous. Even though the entropy of a specific system can decrease, example, when a substance becomes more ordered, this can only happen if the entropy of the surroundings increases by the greater amount. Thus, the total entropy of the universe, system plus surroundings, increases in a spontaneous process. For example, when heat is transferred from a hot object to a cold one, the hotter object loses some entropy, but the colder objects gains more entropy due to the heat increase. The overall result is a net increase in the total entropy of system and surroundings. This fundamental law helps explain why certain processes, like heat flowing from hot to cold, are irreversible, and why the universe tends toward greater disorder over time.
There's a concept that is crucial to chemistry and physics. It explains why physical processes goes one way and not the other. Why ice cream melts, why cream spreads in coffee, and why air leaks out of a punctured tire. It is called entropy. Entropy is a way of measuring how messy or spread out something is. Imagine you have a box of Lego bricks. If all pieces are neatly organized by color and size, that's low entropy. If you dump them on the floor and mix them all up, that's high entropy. Now here's the key. Things naturally move toward high entropy, from order to disorder. For example, an ice cube melts into water because it's easier for water molecules to spread out. One example is your room gets messier unless you put effort into cleaning it. So, in short, entropy is the universe's way of saying mess happens. The formula for entropy is S equals the Boltzmann constant, or the Kb, times the natural logarithm with the number of possible microstate. So the formula expresses entropy as a function of how many different ways the system can be arranged. The more ways means higher, microstates means higher or greater entropy.
Predicting spontaneity. So first and foremost, what is spontaneity? Spontaneity refers to the natural tendency of an event, process, or action to occur without external intervention, meaning it will occur under its own conditions. Now, how to predict spontaneity? To predict spontaneity of a process, it can be done using the concept of Gibbs free energy. It is a thermodynamic function that combines enthalpy, entropy, and temperature. Now, as you can see from my right side, you can see the equation of Gibbs free energy, where delta G, or the Gibbs free energy, is equals to delta H, which is the enthalpy, minus by temperature, multiplied by delta S, which is the entropy. Now always remember that delta G less than 0 is equals to spontaneous, while delta G greater than 0 is equals to non-.
Entropy in action. Entropy plays a crucial role in understanding spontaneous processes which occur without external intervention. For instance, the combustion of fuel demonstrates how chemical bonds release energy, increasing system entropy as gases like carbon dioxide and water vapor form. Similarly, dissolving salt in water highlights how solid crystalline structures break apart, enhancing randomness. In biological systems, entropy facilitates crucial functions such as protein folding, where heat release increases the overall entropy, ensuring proper folding. Other examples like phase changes, ice melting and water evaporating, and energy conversion in engines and refrigerators showcase entropy's universal influence on physical and chemical transformations. A common misconception is equating entropy directly with disorder, which oversimplifies its meaning. While it often refers to randomness, entropy fundamentally represents the number of microscopic arrangements a system can adopt while maintaining its energy. Moreover, entropy is not solely about disorder. It also describes energy dispersal within a system. For example, when heat moves from a hot to a cold object, it increases entropy by spreading energy more evenly. Understanding these nuances helps clarify that entropy reflects both arrangement, possibilities, and energy distribution, making it a cornerstone to thermodynamics.
Entropy is a powerful concept that helps us predict natural processes by illustrating the direction and flow of energy within systems. When we talk about entropy, we're looking at how energy spreads out and disperses. Processes that increase the total of entropy of the universe are favored and happen spontaneously. This means that by understanding changes in entropy, we can predict which reactions will occur on their own. As systems evolve, they naturally move towards a state of maximum entropy or equilibrium. This is where energy is evenly distributed and the system reaches stability.
And that's entropy. Bye-bye!